Now we have also a notion of having some hyperparameters. We saw before the C value for soft margins. We see also the sigma as an influence in terms of Gaussian kernel for SVM with kernels. These are hyperparameters, and these we should adjust them correctly. And in fact, SVM is a complex machine. You know, it is highly dependent on the choices of parameters. So this choice of parameters can have a great influence on the results. In fact, SVM are possibly one of the most powerful models in terms of supervised learning, not dealing with complex things. When we are dealing with images, sound, all these things, neural networks are much better because they are making some kind of representation learning. But if we assume that the variables are well defined, are really capturing the things that are important for classification, for example, SVM are really good to learn good models with not that much data. But SVM are quite complex. And to achieve good results, good generalization results, we need to carefully tune the parameters. And I saw in the past some practical cases where I've discussed or I've been involved where SVM were apparently not really good. They were quite poor at making, at learning something because the hyperparameters were not correctly tuned, there were no like adjustment of these hyperparameters. And then the model was not great for the test at end. So adjusting the hyperparameters for SVM is one of the key elements to making the method to work well. And for instance, with Gaussian kernel, adjusting the parameter C in terms of the regularization, the one that is adjusting the amount of soft margins of data with a XC, a non-zero XC, and the sigma, which is the kernel reach for Gaussian kernel, have a significant impact on performance. And these two are tied. When we change the sigma, the proper C will change. And likewise with different C, different sigmas are working. So these two parameters are really linked together. And sometimes, for some values of these parameters, we can get catastrophic results. With bad values of sigma or bad values of C, the SVM will be really poor in terms of performance. And as such, there are no rules for saying, yeah, this is the right sigma for all the problems. We need to adjust the C and the sigma problem by problem, and this adjustment is mostly empirical. There is some kind of rule of thumb. This is not the only way to do that, but I would say this is the kind of classical way to adjust the hyperparameters of SVM with a Gaussian kernel. Usually we should test different values of C, different values of sigma. These C values need to be at different scales because it's not a matter of having a value of 1, 2, or 3 for C. It's more of having a value of 0.001 or 0.1, 10, 1000. This is the scale that is important. So we need to work in a log scale for C because it's really just adjust the scales of the different elements making the optimization target. And as for the sigma, we need to test it with different values. Possibility is just to look at the sigma, minimum sigma between all the minimum distance between the different pairs of data in a training set. And as such, we use this as a starting point, and we say, okay, let's start with the minimum distance 2 times, 4 times, 8 times. And so growing up until we kind of get over different scales, but more at the power of 2. So this is like the different values we want to test. But the point is that this needs to be adjusted jointly, because these are different parameters. And for one given C, the best sigma is something, but for another C, the sigma to use is something else. So we cannot just adjust one first and the other after that. This is not working well. So we are doing what we call a grid search over that. Grid search is the idea that we are taking all pairs of parameters and testing all of them. So basically we are making a grid. We have all the values for C, for example, all the values for sigma, and we are making we have points of C values we want to test. We have points of sigma values we want to test, and we just fill up the grid about all combinations of C sigma that we want to test them jointly. And we are at just training and testing for each of these pair a model. So basically we do this by splitting the data set in 2. We have X training, X validation. And then we are training the classifier on the training set with each pair considered. So we have different pairs to test. Then we are looking at the classification rate on the validation set that is not used for the training. And we see the performance in terms of generalization. And we pick the pair of C and sigma, for example, that are minimizing the error on the validation set. And we use that pair as, okay, this is the right parameters to use, or those we think are the best one according to our grid search. And then we are retraining a new model from scratch, but now with the full data set. And that is giving us the final model, I would say, the model we should use. So the split in training and validation was just used to test, evaluate the performance with the different hyperparameters. And after that, we will just stick to the right pair and use it as the adjusted hyperparameters to use for training that model. So this is a classical approach. Like I say, it's not the only one. There are other approaches and even some more recent where we are looking at the joint effect or using some kind of fancy optimization approaches that will try different pairs of values in a different way.